Hi everyone, I am Abhinav. In this unit, we will be covering the basic concepts of optimization, which will be useful in this course. So before going into the details, a small disclaimer. This tutorial is meant to be a small introduction. For a complete understanding of these concepts, please refer to any standard textbook. This tutorial is broken into 5 chunks. First, let us start off with the introduction. What is mathematical optimization? Mathematical optimization, according to Wikipedia, is the selection of a best element with regard to some criteria from some set of available alternatives. Now, let us look at the mathematical formulation for the same. Here, we are trying to minimize f0 of x subject to m constraints of the form fi of x less than or equal to bi. f0 is also known as the objective function, fi are the constraints, and x is known as the optimization variable. X is known as the solution for the problem if it satisfies all the constraints and it minimizes f0 of x. Such a solution is known as the optimal solution and is represented by x star. So throughout this tutorial, whenever you see x star, it represents the optimal solution for the optimization problem. Now let us look at some examples where optimization is used. First, data fitting. Data fitting is a very common problem in the field of machine learning. What I mean by data fitting? Data fitting is fitting of a parametric model given some data. So one such example would be linear regression. In linear regression, we are trying to fit a linear model whose parameters are beta i's. So those translate to the optimization variables here. And constraints. Constraints in general encode something like parameter limits or prior information which you want to encode. For the specific example of linear regression, we don't have any constraints. And what would be the objective? We would try to get the best fit for the model. So one way of doing this would be minimizing this error, and in linear regression we've seen how to minimize the squared error. So that forms the objective of the optimization problem. Another example of application of optimization is portfolio optimization. So by portfolio optimization, we mean to optimize the amount of money I can invest in various assets. So these assets could be something like shares from different companies or any other investment options. So the variables would be the amounts I invest in all the options available. The constraints would be the overall budget, the maximum or the minimum investment per asset, and the minimum return I expect from each asset. Objective would be to minimize overall risk or minimize the return variance. We have seen what optimization problems are and we've seen some examples. Now the next big question is, how do we solve them? Optimization problems are very difficult problems to solve in general. Optimization problems are classified into different types based on the properties of objectives and constraints. Some of the examples are linear programs, least square programs, and convex optimization problems. These problems are well studied and can be solved efficiently. Not all class of problems can be solved very efficiently. In this tutorial, we will be covering convex optimization problems in detail. In this tutorial, first we will be looking at convexity. What convexity means and how do we define it. Then we'll look at properties of convex functions, and then we will look at properties of convex optimization problems. And at the end, we'll briefly cover some numerical methods for solving optimization problems. Set C is said to be convex if for all points a, b belonging to the set, the line segment passing through these points should also lie inside the set. So mathematically we can see this as all the points of the form theta a plus 1 minus theta b when theta lies in the closed interval 0 to 1 should also belong to the set C. Next, let us look at the definition of convex combination. A point of the form theta 1 x1 plus theta 2 x2 so on till theta k xk such that the coefficients sum up to 1 and the coefficients are non-negative is known as the convex combination of these k points. Now let us look at examples of convex set. This pentagon is a convex set because any line joining 2 points inside the set lies inside the set, whereas this set is a non-convex set because this line segment which joins 2 points here passes outside the set. Thus these points do not lie inside the set, hence this does not satisfy the definition of convex set. Hence this is not a convex set. Let us look at the definition of a convex function. A function f is said to be convex if the domain is a convex set and if for all x, y which belong to the domain f, the value of the convex combination of these 2 points is less than or equal to the convex combination of the values at these individual points. So what I mean is f of theta x plus 1 minus theta y, that is the value of the function for a convex combination of these points, should be less than or equal to theta f of x plus 1 minus theta f of y. This is the convex combination of the function values at these individual points. So geometrically you can see that the line joining x comma f of x and y comma f of y should lie above the curve. So if this happens, we can see that the value f of theta x plus 1 minus theta y are the points along the curve, and theta f of x plus 1 minus theta f of y are the points along the line segment joining x f of x and y f of y. So by ensuring that this is always above the function, we ensure that the inequality holds, thus making it a convex function. Now let us define what a strictly convex function is. In strictly convex functions, the inequality becomes a strong inequality, that is f of theta x plus 1 minus theta y is strictly less than theta f of x plus 1 minus theta f of y. And now let us define what a concave function is. A function f is said to be concave if minus f is convex. And then similarly we define a strictly concave function. A function f is said to be a strictly concave function if minus f is strictly convex. Now let us look at some examples. First, f of x equal to x square. This is a convex function. From the graph, it is clearly evident that any line joining 2 points will lie above the curve between these 2 points. This claim can also be verified using the definition. The next example we are going to see is that of f of x equal to e power x. Again, graphically you can clearly see that this is a convex function. If you try to prove this according to the definition, you can see that this is not trivial. So we would like to see if there are any other ways to check the convexity of a function. Let us look at the first order conditions for convexity. Let f be a differentiable function, that is grad f exists for all x in the domain of f. So a function f is convex if and only if the domain of f is convex and this inequality is satisfied. This inequality states that the function should always lie above all its tangents. If you look at the right hand side carefully, it is nothing but the equation of the tangent at x comma f of x. and we expect this value to be less than f of y. This is nothing but the condition saying that the curve should be above the tangent. Now let us look at the second order conditions for convexity. Let f be a twice differentiable function. F will be convex if and only if the domain of f is convex and its Hessian is positive semi-definite. So if you look at the second example of e power x, the second derivative is always positive. Hence, it can be proved that it is a convex function. Now we define an epigraph of a function. For a given function f, epigraph of f is defined as the set of all pairs x, t such that x belongs to the domain of f and t is greater than or equal to f of x. So if you look at the graph, you can see that the area above the curve belongs to the epigraph of the function. One important property to know is for a convex function, the epigraph is always a convex set and the converse also holds. That is, if for a function the epigraph is a convex set, then the function is convex. So till now we have seen three ways of checking for convexity of a function. First, you can do the first order test or the second order test, or you can check for convexity of the epigraph of the function. Yeah, let us look at what sublevel sets of function are. An alpha sublevel set of a function f is a set of all points x which belong to the domain of f such that the value of the function at these points is less than or equal to alpha. There is one important property that if the function is convex, the sublevel sets of these functions are also convex. It's important to note that the converse is not true. Now let us look at some other properties of convex functions. First, we look at the operations which preserve the convexity of the function. First, non-negative weighted sum. That is, a non-negative weighted sum of various convex functions will still remain a convex function. Consider fi as a series of convex functions, sigma alpha I fi, where alpha i's are greater than 0, will also remain a convex function. Next, composition with an affine function. Affine function is a linear transformation of x, so ax plus b is an affine function. If f is convex, then f of ax plus b is also convex. Pointwise maximum and supremum of two convex functions will also remain convex. Minimization. If we look at a two variable function f x comma y which is convex, then if we try to minimize the function along any one variable in a convex set, the resultant function is also a convex function. The most important property of convex functions is that the local minima is also the global minima. This is a very powerful result which can be proved easily. This result guarantees that the minima obtained while searching for the minimum of a convex function is the optimal solution. Another important property of convex functions is that they satisfy the Jensen's inequality. This is the generalization of the inequality which we have seen in the definition of the convex function. Here, instead of 2 points, we have n points. So, the value of the convex combination of n points is less than or equal to the convex combination of the values of the function at each of the individual points. A colloquial way of seeing this is that the value of the average is less than the average of the values. Here, by average, I mean a weighted average. Now, let us look at a general optimization problem. Any optimization problem, in general, can be reduced to this form. of minimize an objective function subject to few inequality constraints and few equality constraints. So the optimal value p star can also be written as infimum of f naught of x such that fi of x less than or equal to 0 for I equal to 1 to m and hi of x equal to 0 for I equal to 1 to p. Now the next question is, why did I write infimum instead of minimum? In some functions the minimum might not be attainable. It might just tend to a minimum value but not actually attain it. Hence we write infimum instead of minimum. An optimization problem which satisfies the given three conditions is known as a convex optimization problem. So first, f naught, the objective function, should be convex. Then the inequality constraints fi should also be convex, and the equality constraint should be affine. When I say affine, it should be of the form ai transpose x equal to bi. So one can observe that the domain has become a convex set right now. So the inequality constraints represent a sub-level set of convex function, so it is a convex set, and a convex set intersection with an affine function is a convex set. So why are convex problems interesting? So convex optimization problems are interesting because of the properties of convex functions and the convex sets. So first, the most important property which is useful for us is that if there is a local minima anywhere, it is guaranteed that it is the global minima for the function. So it makes our life very simple and we don't have to search a lot for the global minima. Every optimization problem can be seen in two perspectives. One, the primal form and the dual form. So whatever we have seen till now is generally known as the primal form, and we will now develop the dual form. So why do we need another view of the problem? So sometimes the primal form might be very difficult to solve. The dual form might be easier to solve and also gives us some understanding on how the solution of the primal form may be. So before going ahead, let me just recap the notation which you're going to use. So this is the standard convex optimization problem, and when I say p star, it denotes the optimal value of this problem, and the value of p star is attained at x star, which is the solution, optimal solution. Now let us consider an alternative relaxed problem. Instead of minimizing f naught, we will be minimizing a weighted sum of the objective functions and the constraints. So we will be minimizing f naught of x plus sigma lambda fi plus sigma nu I hi. Here we also have an additional constraint that lambda I should be greater than or equal to 0, and as usual x should belong to the domain. We call the objective of this optimization problem as the Lagrangian. So L is a function of x, lambda and nu, is defined as f naught plus sigma over lambda I fi plus sigma nu I hi. Infimum of the Lagrangian over x is less than or equal to p star. This can be seen very easily, but thing to be noted is this inequality is valid only when x is feasible. So now we define g as a function of lambda and nu as the infimum of the Lagrangian over x. So we've seen a function g which gives us a lower bound of the optimal value of the primal problem. So if we try to maximize this function g, we will achieve a very good lower bound of the optimal value. So this is what is known as the dual problem. So maximizing g of lambda comma nu such that lambda is greater than or equal to 0. The optimal value of this problem is attained at lambda star and nu star. We can see that this function g is concave irrespective of the form of the primal problem. So if you go back and see, we've started with the general form of the primal problem, and we've reached with g which is concave. So g can always be solved. The optimal value of the real problem is denoted by d star. So now we would like to see how far is this d star from the actual value p star. So p star minus d star is known as the duality gap. The next obvious question is to find out when this p star minus d star will be 0 and when it is not. So whenever it is 0, it is known as the strong duality, and when it is not, it is known as the weak duality. So next, we will try to further characterize when what can occur. So first we can see that p star can be written as infimum over supremum of L, and d star can be written as supremum over infimum for L on appropriate variables. So when the strong duality holds, we know that p star equal to d star. So you can see that the order of the infimum and supremum can be interchanged and it's equivalent. So this means that at the same point we have a maxima in one direction and a minima in another direction. So it is a saddle point. So we have one good result here, that is whenever there is strong duality, optimal variables occur at the saddle point of the Lagrangian. Now let us look at sufficiency conditions for strong duality. So we look at latest conditions, which gives us conditions for a convex optimization problem to be strongly dual. So latest condition states that for a convex optimization problem, if there exists an x such that it belongs to the relative interior of the domain, such that fi of x is less than 0 and h of x is equal to 0, then strong duality holds. So here we require the inequality constraints to be strictly unequal, and the point should belong to the relative interior and not the boundary. So this latest condition states that for any convex optimization problem, if there exists a point inside the feasible region, then strong duality surely holds. So note that this is only for convex optimization problems and not a general result. So now we look at complementary slackness. Assume strong duality holds and x star is the primary variable and lambda star nu star are the dual variables. So when I say strong duality holds, we know that f naught at x star is equal to g at lambda star nu star. Okay, so by expanding g as by its definition and looking at some simple inequalities, we reach to a conclusion that for all I, lambda I star fi x star should be 0. Okay, so basically we know that fi of x star is less than or equal to 0 because x star is a feasible value. So whenever fi of x star is not equal to 0, we know that lambda I should be equal to 0. So this is known as complementary slackness, that is either lambda I star should be equal to 0 or fi x star should be equal to 0 when strong duality holds. Now we look at Karish-Kuhn-Tucker conditions, also known as KKT conditions. So these provide us the necessary conditions for a point x star lambda star nu star to be optimal. So consider any point x star lambda star nu star. If it has to be an optimal solution, these things have to be satisfied. So first, stationarity. So since we've already seen that at the optimal point, L has a saddle point, so the gradient at that point should be 0. So that is trivial to see. Then primal feasibility and dual feasibility should hold. That is also obvious. And then we've seen complementary factors, as we've seen previously, will also be valid at this point. So just to reiterate what we've already seen, if x lambda nu satisfies strong duality, then KKT conditions hold. So these are just necessary conditions and not sufficient. But for our optimization problem, when Slater conditions are satisfied, then KKT becomes sufficient also. Now We'll look at some examples. So first is the most popular example of least squares. So we are trying to minimize a least square function. So we are trying to minimize this 2 norm of ax minus b with no constraints. So you can clearly see that this is a convex function and has no constraints. And we've already solved in this thing in while solving linear regression to get x star as a transpose a inverse a transpose b. So so this is a very trivial convex optimization problem which you are able to solve by just by differentiating. Now let us look at another example. So here we are trying to minimize x1 square plus x2 square subject to these two linear quadratic constraints. So if you look at these constraints carefully, both of them are circular regions, one centered at 1 comma 1 and the other centered at 1 comma minus 1, each of which is radius at 1. So if you just plot them and see that you can see that there's only one feasible point, that is 1 comma 0. So trivially the optimal value will become 1. But now let us do the analysis which you have learned on how to do and then try to arrive at the same answer. So first, when you have a convex optimization problem, or for that matter any optimization problem, the first thing you do is write down the Lagrangian. So here the Lagrangian will be x1 square plus x2 square plus lambda 1 times the first constraint plus lambda 2 times the second constraint. So now that you've seen the Lagrangian, let us try to list out the KKT conditions. So here the first two are the primal feasibility conditions, the second two are the dual feasibility conditions, and the next two are obtained by differentiating the Lagrangian with x1 and x2 respectively, and the next two are obtained by writing the complementary slackness equations. And we've seen that there's only one feasible point 1 comma 0, and at that point these conditions are not valid. Like you get contradictory answers for lambda 1 and lambda 2 when you try to solve. So that is KKT conditions are not valid. But this is tricky. So we've already seen that we have an optimal value but KKT conditions are not satisfied. We'll try to see why this is happening here. Okay, now let us try to investigate what exactly is happening. So we'll try to solve the dual problem now. So for solving the dual problem, we have to find the maxima for g. So first let us find out what the function g is. G is infimum of the Lagrangian over x. So we'll try to take derivative of L with respect to x, solve it, and then we arrive at this g function which is a function of lambda 1 and lambda 2. Now you can see that this is a concave function which is symmetric in lambda 1 and lambda 2. So we can just substitute lambda 1 equal to lambda 2 equal to lambda 1 and then go ahead. So when we do that, we get this 2 lambda 1 by 2 lambda 1 plus 1 as the g function. So if you see that under the limit lambda 1 tending to infinity, g tends to 1. But otherwise there is no maxima achieved. So under asymptotic conditions, p star equal to d star equal to 1. Because these points are not being attained at a point, KKT conditions and Slater conditions are not satisfied. So this example is to show you that just solving KKT conditions or checking for Slater conditions is not sufficient. You might have to solve sometimes the dual problem and see what exactly is happening. So we've seen the mathematical characterization for optimization problems. Now we'll try to see how to solve them. So there exist many standard algorithms to solve optimization problems once you take them to standard form. So for linear programs there is this well-known simplex method, and the most popular methods for solving general optimization problems right now are interior point methods. We'll not be covering these methods in detail at all. We'll be looking at a simpler class of problems, that is that is optimization under no constraints. So that is, given an objective function under no constraints, how can we solve this? We look at algorithms for these. So to do this, there exists a lot of algorithms: gradient based methods, genetic algorithms, and simulated annealing. First, we look at gradient based methods, which are very popularly used in machine learning. So first, let us look at a proper mathematical definition of unconstrained minimization. Consider a convex function which is twice differentiable, and we want to find the minimum of this function. So assume p star is the minimum and it is finite and it is attained by f. So we want algorithms which start from some point and give a series of xi's such that the value of f of xk tends to this optimal minimum p star. So these algorithms require one condition, that is, the sublevel set should be closed. So what exactly this condition means is, so when I start from x0 and I go to some other point which is less than this, so basically at each time I'm trying to reduce the value of f. So from x0 to I go to x1 where f of x1 is less than f of x0. So that is, this belongs to the sublevel set of f at f of x0, and this point x1 should be inside this set. So that we just need this condition so that we get a chain of points which are in the domain of the function. So now we look at one of the most popular algorithms known as gradient descent. So this works in convex problems where there exists a minima, and you start from one point at the top and go down according to the gradient. So if you see this visualization gives you a three-dimensional surface which is basically f of x1 comma x2, say. So if you start off, say, f of x1 comma x2 at the top point, and we take the gradient there and move along the negative direction of the gradient slowly, as we keep going down we reach the bottom of this curve. So and the bottom is where the minima exists. So at the last point the gradient becomes 0. So this is the motivation for gradient descent algorithms, that is, by going along the negative direction of the gradient we reach the minima in convex functions. So now let us formally look at gradient descent. We have intuitively seen that if we move in the direction of opposite to the gradient we will reach the minima. So we'll state it as an algorithm. So if you start at x0 in the domain of f, you can update in every iteration x as x equal to x plus t times delta x, where delta x is minus gradient of f of x. So essentially what you're doing is you're moving along the negative direction of the function in some step size of t. Basically this t is a multiplicative factor which will magnify or minimize the step size which you're taking in the direction. So the next question is, how do we choose t? Should t be constant? So in the ideal case t should be dependent on the curvature of the function. So if you look at the graph in the previous slide carefully, so wherever there is low curvature you could afford to take larger steps, and wherever there's high curvature at the bottom, especially where there's minimum, you should take small steps of t so that you don't jump over the minimum value. Methods which choose t according to this criteria are out of the scope of this tutorial. So but we'll just answer this question: is t constant enough for us? So in most conditions a small t, if you take a small enough step size, it is fine and you will hit the minima very reasonably, very close to the minima. So in practice a constant t works. So we will end this tutorial session with this. So the main take home of this tutorial session should be what optimization problems are, what is the general form, what are convex optimization problems, what is duality, what is strong duality, what is KKT conditions, and what is later conditions. So knowing these will be enough for you to navigate through whatever optimization concepts which you'll come across through this course. But ideally you can look up other resources online if you're not clear with these basics still.